So good afternoon, ladies and gentlemen. My name is Brian Zaheda Casada. Here with me we have Endrit Nezaj, we have Emmanuel Fitzakis, and we have Kenneth Tai, and we are Team Bakke. And our project is smart glasses with image recognition software. So without much further ado, let me start off with an outline. So this is our outline. These are all the topics that we're going to be covering today. And to start off, we're going to be talking about each team member, their expertise, and their role in our project. And we're going to have Kenneth explain this.
All right, so over here we have Brian. His role is project manager and his expertise is experience with cybersecurity. We have Emmanuel. His role is software lead and his expertise is experience with embedded system. We have Endrick over there. His role is hardware lead and his expertise is experience with complex circuit. I'm Kenneth and my role is software and hardware. And my expertise is experience with network architecture.
Okay, so now we're going to talk about our project motivation. Many of us know people that work in law enforcement or people like officers, cops, anybody like that. And if you do know somebody, you know that sometimes tensions can get really high when the law enforcement comes into contact with civilians for both parties. You know, for the cop, if they're pulling somebody over, they don't know if they're pulling over an everyday guy who's just late to work who's probably speeding, or if they're pulled over a criminal with a previous criminal history who's, you know, they don't know, they're not sure. And for the civilian, you know, sometimes they question why they're being pulled over or why they were stopped, and sometimes they get anxious and it leads them to do things that they wouldn't do normally. And over here in the picture, you can see this is an illegal immigrant who was worried and fearful for why the cop pulled him over, and he decided to pull a firearm, and now an everyday like pullover situation became a fatal shootout now.
So next we're going to be talking about how we selected this project. As you saw our motivation for our project, but now we're going to talk about how we got to the solution that we got to. So we started off with an idea of using goggles. So these goggles would have two LED screens that would be reflecting off of some glass lenses, and it would show the user what the information they want to display, and it was going to be like an augmented reality headset. Our second option was going to be a Bluetooth-enabled microcontroller on the glasses that would send the images taken by the camera to your phone, and the phone would do the processing instead of the camera doing the processing themselves. Lastly, we have our final solution, which was the smart glasses solution, which we're going to be talking about more in depth. But the way we got to our smart glass solution is by using the weights calculated on our analytical hierarchy process. And now we're going to be talking about our project summary.
So our project summary. Our project is creating smart glasses that would be able to identify someone in mere seconds. We plan on achieving this by creating real-time facial recognition software that would be able to identify a person and display information about the person on the glasses. This will be extremely useful for the law enforcement agents and pedestrians whom are at danger when a traffic stop occurs. However, this project has the potential for much more and ideally will serve as a platform for developers to design applications to help augment society for the better.
And we would like to point out that the originality of our product is that most previous products have very good facial recognition software, but we're trying to make one that's going to be as accurate as possible due to the circumstances that we're going to be using them. And they're going to be displaying the results at a quick manner in order to have the officer have the information right there at readily available. So next we're going to talk about global social and societal impact that our project will have, and Andrew will be talking about this.
So the impact when we successfully develop accurate and real-time facial recognition capabilities will carry great societal solutions to current issues. In an environment where, you know, like I said before, when the tensions get high, you're not sure what you're going to deal with. So any solution that can remove any kind of ambiguity or any kind of uncertainty in the situation would definitely make a world of difference. If law enforcement was better informed in exactly who they pulled over quickly, it would allow the officer to know how to better deal with the situation at hand, and it would remove some of that ambiguity. The main goal here is to basically reduce the amount of tension, because as soon as the officer knows who they're dealing with, they can move forward.
So now it's time to talk about the design requirements and specifications of our project. So I'm going to start off talking about our marketing requirements. Our first marketing requirement is to make sure that our product is lightweight. Of course, if we're using glasses, we don't want glasses that are heavy. We want to make sure it's comfortable for our users. So that's one marketing requirement, and we got to these marketing requirements by interviewing our friends and colleagues that are part of law enforcement and our classmates that are former veterans. So the first one that they identified was that it has to be lightweight in order for it to be comfortable. Next, it must be accurate. Like we're going to be talking about in our ethical analysis of the project, this product must be accurate and reliable because we don't want to have it produce misinformation and misidentify a person. It is important that it's unobtrusive. So since these are glasses, we don't want to have our information displayed on all of the lens. We want to make sure that it's a certain part of the lens so it doesn't obscure the view of the officer or the users themselves. Fourth, it must be easy to use. We want to make it accessible because this is going to be used by a wide range of different users, so we want to make sure that every user can use it easily and it's not a difficult learning curve for them to use it. Next, we want to make sure that it's durable. We want to make sure that the product can withstand all daily usage. When you use a product in daily living, like a watch or any type of wearable, it's durable enough to withstand all weather conditions and everything that comes with daily life living. And lastly, the results must be produced quickly. Like we said with the use case earlier, of a traffic stop, this information must be readily available to the cop, and it must show up immediately on the screen. So that's something that we want to make sure that is part of the market requirements. Now, our engineering requirements were developed using the marketing requirements. So our first engineering requirement is that the facial recognition software should be greater than 98% accurate. Like we said, we want to make our product very accurate in order to not misidentify a pedestrian. Next, the output from the image recognition software should be displayed in less than 5 seconds. Like we said, we want it to be readily available and quickly displayed. We also want the system to run in 5 volts. We have identified that 5 volts is the necessary voltage that the system needs in order to run all day. Next, we want to make sure that the images from the camera should be set every 5 milliseconds. We want our image recognition software to have enough data in order to process the image accurately, but also we don't want to overflow with the data input. We want to make sure that it's enough for it to process it accurately, but not too much where it's going to crash. Also, we want to make sure that the software is simple enough to update. As we're going to see in the codes and standards, we want to make sure that the law enforcement agencies are able to update this easily due to some cybersecurity requirements that we have to fit. And the system should be less than 1 pound. We want to make sure that it's lightweight and comfortable for the user. And lastly, we want the display to occupy less than half of the right lens. We want to make sure that it doesn't obscure the user's view. Here's our engineering marketing trade-off matrix that shows the correlation between the engineering requirements and the marketing requirements. And an objective tree. Here we have the ranking of the different engineering categories or engineering requirements, and we found that accuracy is the most important one because it's the one that's going to bring the most ethical issues to our product, so we want to make sure that our system is extremely accurate. And now I'm going to have Emmanuel Fitchakis explain the theory behind all of our product.
Yeah, so for our current software version, there's 3 key players right now of outside frameworks that help us recognize faces, get facial landmarks, and store large data sets. So we're using DLib, which is a pre-trained machine algorithm that allows us to recognize when a face comes into screen. And then our next framework is facial recognition, which allows us to get the facial landmarks. Now this is what separates somebody from somebody else, and it gets, as you can see in this large array, it gets all of the important facial landmarks and stores them in a 2D plot. And right here is just a plot of the larger array. It kind of creates a mask. This mask separates somebody from somebody else. And when a new face comes into frame with the existing array, it'll get the face, it'll get the facial landmarks, and it'll check the facial landmarks against the existing, and if it exists, it'll return positive, or it will return an unknown that it's not part and it's a different face.
And now our system description. So not included here is the power supply because we're treating that as more as an accessory of the product, but the overall product is our smart glasses, and it's composed of 4 important components. Our Nano Neo 4, which is going to be the brains of the operation. Transparent LED display, which is going to be the way that we display the information to the user on the glasses. The camera, which is going to be the way that the system is going to be ingesting the images. and the battery, which is going to be powering the whole operation when it's mobile. And our data flow diagram is very simple as well. The camera will be taking the images and it's going to be sending it through a universal serial bus to the NanoPioneer 4. The NanoPioneer 4 will then send this information to the image recognition software, and then the image recognition software will give out the results, and the results will then be displayed to the transparent OLED display using serial communication. Here's the functional decomposition graph. So here we're going to see an overview of how the smart glasses takes input and output. So it's inputting 5 volts and images, and the output is going to be the results of the product. Next, we're going to see that the images are going to be going to the NanoPi Neo 4, and it's going to be also taking an input of 5 volts, and it's outputting the image recognition software output, which is going to be the input to the transparent OLED display. And also the input to the transparent OLED display is some voltage, not as much as 5 volts, but it's going to be enough to power it up, and then it's going to be the results on the display. Now we're going to have Andrew talk about the hardware and design implementation.
Okay, so for our power supply right here, this is our input, which is 120 volts AC from a regular wall outlet. It's going to go through a 10-to-1 transformer, drop it down to 12 volts. This is going to convert it from AC to DC, basically give us an output of 5 volts and 3 amps, which is our ideal values. This chip right here will drop the 12 volts that comes after the transformer, drop it down to 5 volts by default every time. And that's right here. That's the 12 volts to 5, and then the 3 amps, which is our ideal output to run the microcontroller and the glasses.
Now we're going to have Emmanuel Fitchsockets talk about the software design and implementation.
So right now we have 2 versions of our software, and the only difference between the 2 is how they get our images for our data set. So the one version, we have a hard folder in the C directory that the Python script looks in, gets the images, encodes them, and puts them in a data set. And then our second version gets it from MySQL and does the same thing. So what's happening is, once we get our faces, once we get the facial landmarks and put them in the data set, we use OpenCV to start a live stream for our external camera. We use dlib again to see when a face comes into frame. We get the facial landmarks of this face, and then we test whether it's the array of the facial landmarks are in our existing array, and if it's not, then we just we output the result whether it's known or unknown.
So we've been talking a lot about the theory behind it and the design implementation, but now we're going to show you how we actually implemented it.
So over here you can see the AC adapter we were using. That's the power supply that we created with the 12 to 5 voltage drop, and we connected that to an external battery power, which was then able to charge the battery. And here you can see the same setup, but just now we're going to plug it into the Raspberry Pi, which is the microcontroller that we temporarily used. And after we turn it on, you can see the Raspberry Pi powers up. And it's booting up right now.
So the software, we're just going to be showing the external camera. Brian's known in the data set, so we should get something that outputs Brian's name, as we'll see right now in the console. And we return Brian, and then Brian actually holds up the camera to his face while he's looking away. So it pops up as unknown, and then my face, who's also in the database, shows my name. We plan to implement a neural network. That way we get more pictures as one input. That way we reduce the false positives. So iterations. So for software, we wanted to make sure what we wanted to do was achievable. So we sat down on our regular machines, like our PCs, and we programmed it, and it was all fine and good. But the problem with that was when you move it to a microcontroller, you're working with less RAM, less processing power and memory. So that's when our second iteration came in, and we had problems trying to port our software onto the microcontroller with our existing libraries. So we had to use virtual environment wrappers to get our dependencies, and we had to optimize our code to slow down our latencies with these mic cameras.
And so for our hardware iterations, just to get an idea for what kind of values for the voltage and the amps that we would need coming in, we tested out a simple power supply with 12 volts and 1.5 amp input, but it wasn't nearly enough because we were only getting an output of 200 milliamps, which wasn't enough to power the Raspberry Pi. In the second iteration, we bumped it up to 3 amps, which was then enough to power the Raspberry Pi, which you guys saw in that video, which is when the Raspberry Pi booted up.
We also want to point out that, as you saw in the video, there was a larger power supply in the left side, and that was because we were unable to get a 10-to-1 transformer in time for demonstration. However, we wanted to not have that as an obstacle. We actually wanted to work around it, and we decided to build at least half of the circuit and use that power brick as a representation of what we will be building during the winter break. And we got the power level from Dr. Wong that, as Andrew mentioned, is 12 volts and 3 amps. This is what we're going to be getting an output from our 10-to-1 transformer and our diode circuit as well. And now we're going to have Kenneth talk about testing.
So over the semester, we performed numerous amount of tests to ensure that it met our requirements that we set in the beginning. So the first one we have is the facial recognition software. We are planning on creating a neural network that will be trained in order to make our facial recognition software more accurate. Our second one is the facial recognition software in MySQL. We are planning on testing this again after the implementation of the neural network. But ideally, we will create dictionaries for each recognized face with their query results. In order to avoid building up on a big cache, we will restart it after every 10 seconds. Lastly, we have the power supply. We are planning on using the voltage regulator since the LM7805 peaked at 1.5 amps. Lastly, we have the integration test. What that is once we have all those three figured out and made, we will implement them into powering the Raspberry Pi and have it running again.
So now we're going to talk about our project timeline. So here's a brief overview of what our project timeline is, but to go more in depth, this is our hardware timeline. So far we've completed a majority of the work. So we've created our prototype. The next semester we're going to be implementing the transformer and building this all on a PCB and ordering that PCB. So we've allocated the accurate amount of time to have the PCB come in before the final presentation. Next, we've also implemented this semester the camera, which is a major component of it. We've tested it and we've seen that it does work with our software. Next semester, all we have to do is connect the camera to the new microcomputer, which is a very similar architecture to the Raspberry Pi, so that's not going to be a hindrance, and we're going to test it out. So this is a very simple task. Transparent OLED implementation, we've tested this out on the Raspberry Pi with not the transparent OLED, but a similar LED display, and it does work. So all we have to do is order it, and it's going to be coming in, and we're going to be connecting this. This section we're going to be doing over the winter break, in order to ensure that we have it ready to test for our spring semester. Lastly, we're going to be building an enclosure. We're going to 3D print an enclosure in order to make our product not only actually work, but also we want to have it look aesthetically pleasing. These are glasses, so we want to make sure that these components don't connect to the person incorrectly, and we want to make sure it's all together and in a concise format. Next, facial recognition software. We've done a majority of the work. Next semester, all we have to do is implement the neural network and test it. So we want to test the implementation of the neural network and make sure it works the same way that our previous version worked. And actually work better because it's going to have a better accuracy. We've implemented our database. Our database is nice and set. We finalized it. All we have to do next semester is install MySQL connector, which is very simple, into the NanoPi Neo 4 and do a few test queries when we implement into our facial recognition software. And we've allocated a large chunk of time to testing because we really want to make sure that our product is done and complete and works very well for the final design. So I want to make sure we have a complete product that in the case that it wants to be bought by someone, it's ready to be bought. And we set these 2 milestones. These 2 milestones are really essential in order for us to know that we can move on with this project and make sure that it works. So the first milestone is to get our facial recognition software to work, to run on a Raspberry Pi. If we can get this to work, that means that we're going to be able to get the right results and get the right display to get the right results, which we got to work. And we created a power supply for our glasses, so we got this, and we met all of our milestones. Now for cost. We've reached total cost that is much less than the $250 allocated for us from Manhattan College. So we plan on continuing on this journey, and also we plan on not including the 3D printing cost because it's going to be done in the school. But if needed, we have enough budget. We've given enough budget space just because in case there's money needed for other components that we may find needed in the future. And now we have code standards and constraints. So here we have a few standards that I've identified as very important in order for our project to run. So the PEP 8 Python standards, we must abide by these standards since we are using Python as our main coding language for our project. We are considering this by using standard Python libraries and formatting our software to fit these standards. So we want to make sure that we follow these standards and make sure that we're up to the Python standards. Next we have the INCITS 385/2004 standard, which is a standard that we must use in order for our facial recognition software to fit the standard. We need to have our images fit a certain amount of constraints, like the lighting of the picture, the framing of the picture, the cropping, and how far the picture is taken. So we want to make sure that it follows the standard, and we're going to make sure that our images follow this. The NIST 853, this is a security standard in order for anything to be used as in a government setting. So we're going to make sure that our software is secure and it's secure against SQL injections. This also falls in line with our New York State secure coding standard. We want to make sure that code is secure. This is going to be in the hands of law enforcement agents. So anyone's going to try to maliciously attack it, so we want to make sure it's secure and it cannot be attacked from a malicious user. Lastly, we're going to be using the New York State Enterprise Mobile Management Technical Standard. So we want to make sure, that's why one of our engineering requirements and our marketing requirements was to make it easily updatable. As a government entity, they're going to need to update our product in order to, and it has to be done easily because if there's a vulnerability in one of our libraries, it has to be easily updated in order to make sure that no malicious user can maliciously attack the product. So next we're going to have our ethics analysis of our project by Andrew Nessage.
So we want to make sure that our design follows the IEEE Code of Ethics, especially these 3 up here. We want to make sure that the tolerance level for our product is high so that there's no false positives. We don't want to wrongly accuse somebody for something that they hadn't done just because they look like somebody else. Our design needs to produce accurate response regardless of the person's race in order to avoid, again, those false accusations and ruining reputations. We will make sure that the code on the glasses is secure enough in order to follow Code of Ethic number 9, which is to avoid injuring others of property, reputation, or employment by false or malicious action.
So over the semester, we've achieved a lot. However, we've encountered a lot of problems. We eventually had to fall back to our backup plans, sometimes to the backup to the backup. Eventually, we were able to meet our milestone. So although this semester is coming to an end, we have a lot of work to do over the break. So by next semester, we want to have the NanoPi Neo 4 integration, transparent OLED integration, 3D print enclosure creation, and finalizing our power supply and battery integration.
And as Kenny said, even though we've had some obstacles, we've worked around these obstacles to make sure our project is still following the accurate timeline. We'd like to thank you all for taking the time to be with us, and we hope that you can follow us on this journey to make our streets safe with our smart glasses. Thank you. Any questions?
Just a quick one on the OLED. I'll make this premature. Size, resolution, and how do you connect it? Can be connected. The size of the OLED screen, resolution, and physically how do you connect to it?
Okay,
So right now we're using an external USB camera, and the camera has, it's 2 megapixels. So, but in the code we scaled down the resolution. That way we're not taking all the megapixels. We only want, or we scale down the resolution because if we work with a larger resolution, we'll get more lag and latency. So it's done through the code, and the connection, like I said, is just USB.
And with respect to the transparent LED that you asked, it's a very small transparent LED, and it's being connected through the UART ports, and it's going to be using serial communication to connect to the microcontroller. So it's not going to be using USB, it's going to be using the pins on the microcontroller itself, and it's just going to be, it's very small, it's about this size, and it's going to show up, it's text only, so we're not going to, we're going to make sure that it doesn't affect the user's eyes. That's all. Any other questions?
Yes, so you mentioned about the visual recognition accuracy. So what's your plan that you increase accuracy?
So right now, as we both saw in the lab, it's when you kind of turn your face out of the frame, we don't get anything. We don't get a false positive. We don't get like a false negative. So what we want to do is we want to use a neural network instead of these outside frameworks. We want to work with TensorFlow and Keras to give more images for just one person, because right now we can only give one straight image to the library. So if we give a side profile straight and then another side, we'll be able to get more false or more positives, like right positives, based on the orientation of the face. So that's what we're talking about with accuracy.
Yeah, and we want to make it recognize more facial features better, because there's people I look similar to, I know someone that I look very similar to, so I want to make sure that the facial features that it sees, and we're training our neural network to find these locations and landmarks so that it cannot misidentify each of us. It'll identify myself as Brian and this person and this person. That's it. Any further questions? All right, perfect. Thank you very much. Hope you guys have a wonderful day.